Okay, this is the lecture video for Mac 1140 Pre-Calculus. We're in section 5.2, and in this section we're going to be taking a look at the various definitions and theorems concerning one-to-one functions and inverse functions. We're going to take a look at how to determine whether a function is one-to-one. And we're also going to see how that leads into the ability to find the inverse of a single function. And then we're also going to look at how to determine or verify whether two separate functions are inverses of each other. Okay, so we start off in this section looking at the definition of one-to-one. I'm going to reword it in my own words, but this is the way your book is giving it. And they try to state it in two ways. A function is one-to-one if any two different inputs, those are the x values in the domain, correspond to two different outputs, those are the y values in the range. That is, if the first x value and the second x value are different inputs of a function, f, then the function is said to be one-to-one if the corresponding y values are also different. So here's another way to say that, and then I'm going to tell you what the easiest way is to check whether a function is one-to-one. So restated, as long as each x must have a unique y partner. In other words, each x can be associated with one and only one y partner. That's what it means to have a unique y partner. Must have a unique y partner. And it goes back the other way too. Each y must have a unique x partner. Easiest way to check whether a function is one-to-one when you are given a domain and a range, a set of x input values and a set of y values, that's the domain and the range, is to just make sure that all the x's are different. Because if all the x's are different, there's no way that any x could be associated with more than one y partner. So you'd be checking that each x has a unique y partner. So you have to make sure that all the x's are different. And that all the y's are also different. Okay, easiest way to check whether something is one-to-one. Okay, and when you do this, make sure that all the x's are different and all the y's are different. You are checking this, that each x has a unique y partner and that each y has a unique x partner. You're checking both of those at the same time. It's just an easier way to do it. Okay, let's go ahead and look at the theorem associated with this definition. In order for you to check whether a graph is one-to-one, so this is for when you're given a set of x and values in set notation or as ordered pairs. But when you're just given a picture of those ordered pairs, then you find yourself with just a graph. And in that case, the horizontal line test is what's going to check that each x has a unique y partner and that each y has a unique x partner. Okay, when you draw a horizontal line through the graph, that horizontal line should only touch the graph in at most one point. It should only intersect it once. So we're also going to be using that to check one-to-oneness. Okay, let's take a look at some of the examples where we are using definitions and theorems having to do with one-to-one. being a one-to-one function as well as being an inverse function. Those definitions are below. So in example 1, all they're doing is you are completing the sentence that has to do with the definition for one-to-one. In fact, you can see that you can find the same wording right in the definition. If the first x and the second x are two different inputs, and you can see that wording right here. If the first x and the second x are two different inputs of a function, then f is said to be one-to-one if the y values corresponding to those input values are also different. So you're going to complete the sentence using this. So in example 1, if x evaluated at the first, if f evaluated at the first x value is also different than the function evaluated at the same x value. In other words, the y values are also, the y partners are also different. Okay, in example 2, this has to do with the theorem, the horizontal line test for testing one-to-oneness. If every horizontal line intersects the graph of a function, in other words, no matter how many horizontal lines you draw, all of them should intersect the function at no more than 1 point. That's just the theorem that you see right here. And when that happens, f is said to be an inverse function. I don't have enough room to fit that in there, so I will just write it down here. In example 3, if f is a one-to-one function, and f of 6 is equal to 4, then what is the inverse of 4? Now this concerns inverse functions. That's what they're trying to get you to do, and that's this symbol. You know that they're talking about inverses when you see this symbol, and you can just see the definition below, right below this problem. They talk about the definition of inverses. The reason we learn how to determine whether a function is one-to-one, either when it's given as a set of points or when it's given as a graph, either way, is because you need for the function to be one-to-one or else it doesn't have an inverse. So we first learn to determine that, then we get into inverses. Okay, so basically what's going on with an original function and its inverse function is that the x's and the y's switch responsibility. And that can be said in a multitude of ways. I'll show you a variety of problems where we're demonstrating that. The x's and the y's, in other words, the domain and the range, they switch when you're going from the original function to the inverse function. And so like I said, they can give you different kinds of problems where you're showing that, such as example 3. Okay, in the original function, this would be the x and this is the y. So when you go to the inverse, they switch. This y becomes the x and this x becomes the y. And this answer right here, the answer is the y. So notice that they put the 4 in here. Here it is now. And now the 6 goes out here. So that's one example where you're showing that you understand that the relationship between the original function and the inverse is that the x's and the y's switch. And that's what this definition says. Suppose y is the original function f of x and it's one-to-one. The correspondence from the y values, the range of f, to the domain of f is called inverse of f. The symbol f, what looks like a power of -1, but really in this case it's just used as the symbol for inverse. It does not mean raised to a power of -1. The inverse symbol for the function is used to denote the inverse function of the original function f. In other words, if y is the original function f and it's one-to-one, f has an inverse function symbolized like this, and x is equal to the inverse of y. Now that's kind of hard to understand the way they write that, but basically what that means is that the x's and the y's, or in other words you could say the domain and the range, they switch responsibilities. You could say it either way. Okay, theorem based off of that definition. the graph of a one-to-one function and the graph of its inverse are symmetric with respect to the line y equals x. That means if you put the graph of the original function and the graph of the inverse function on the same grid, which you will be required to do, you will find mirror images on either side of the line y equal to x. In other words, you could draw a line y equal to x, which is just a slanted line that goes right through the origin, and it would split the two graphs into two mirror images, so that if you crease your paper, fold your paper on y equal to x and open it up, you have two images that superimpose. Okay, moving to example 4 here. In example 4, whoops, went a little fuzzy. Let's see if we can fix that up. There we go. In example 4, this says if the inverse denotes the inverse of the original function f, then the graphs of the original function and the inverse are symmetric with respect to the line y equal to x. And this is just a picture of that. Here's the original function. Here's the inverse function. And if you have any kind of spatial orientation, you can maybe see this. Otherwise, you could just try it physically. If you crease your paper right here and fold this image on top of the blue image, they would actually superimpose each other, which means these two images are mirror images. The images or the graphs of f and f inverse are mirror images on either side. We use the word about to mean on either side of. About the line called y equal to x. And that's always true for any original function and its inverse. And all they did for this inverse function is they took all the points here and they switched the x and the y. And that's how they got the picture of the inverse. Okay, stated on in a broader sense, they're just saying that the x's of the original function, also called the domain, are the range of the inverse. So if you know what the domain of the original function is, you know all the x's of the original function, then you also know the range of the inverse. You know two things by knowing this. If you know what the range, all the y values are of the original function, then you also know the x values of the inverse. And we're going to use that as we answer the questions in examples 5 through 8. Various examples from my math lab where you're using this definition of the inverse. So example 5 says, if the domain of a one-to-one function called f is 7 to infinity, then the range of the inverse, which is just this reiterated, the domain of the original, that's this right here, is equal to the range of the inverse. So when you go to complete this, you are using this right here. So, and that says the domain of the original and the range of the inverse are exactly the same. So if one is 7 to infinity, so is the other one. Going on to example 6. Another example of understanding the relationship between the points on the original function and the points on the inverse. So here is a point on the original function f, and we want to know, if you know that this is a point on the original on the graph of the original function, or it belongs to the domain, then what can you be sure of as a point that belongs to f inverse? Well, just again, switch the x and the y. This becomes the y, this becomes the x. So the answer to this would be -2, 5. This would be like a multiple choice question, and that would have been one of the choices in my math line. Example 7. Suppose you have a one-to-one function with this is the domain, Okay, domain of the original function, and this is the range of the original function. Which of the following, and that would have been a multiple choice question, would be the domain of the inverse? Remember, the domain of the original is the range of the inverse. Slide that down so you can look at it again. The range of the original is the domain. So domain becomes the range becomes the domain as you go from the original to the inverse. Now their question is, what is the domain of the inverse? Well, that's equal to the range of the original. Okay, domain of the inverse is equal to the range of the original. Okay, so all we have to do is come back here and look, what is the range of the original? Here it is, right here. Okay, so that's going to help us to get this domain. So let's come down here and state what the domain is. Now remember, you got to be careful here. I know that this range is stated using y's, and we are going to use these restrictions and this number, but you are now talking about the domain. So you have to state this in terms of x's. So be careful with that because you're going to be tempted to just copy it. So any x's such that these stipulations are obeyed. X can be any x such that x is not equal to 6/7. Okay, so we did use those range values to get our domain of the inverse, but we had to switch the letter that was mentioned there because we're now talking about domain. Here's another type of question. In example 8, it says determine whether the function is 1-to-1. And I was stating that on the very first page when I gave you the definition of a 1-to-1 function, that the easiest way to check whether each x, these are all the x's, anything in the domain is x's, and anything in the range is the y's. The easiest way is to make sure all your x's are different and all your y's are different, and they are. You don't have any name mentioned twice, so this is, these are all different, and these are all different, so, and I can put y just in case you look at this later. Okay, since all x's are different, and all y's are different, that means that this function represented by this set of by this domain in this range, this function is 1-to-1. Because what you're proving when you look at all the x's being different and all the y's being different is that would force each x here to have a unique y partner. It's paired to one and only one y value, just like this is paired to one and one y value. That would be true of all these x's, but it would also be true of the y's, that each y only has one partner. So that's just a quick way to check all that. So the function represented by this domain in this range is 1-to-1. Okay, moving to number 9. In problem number 9, this time they give you a set of ordered pairs. So you do have a domain. That domain's 2, 3, -8, and 6. You have range values 9, 6, 14, and -17. And what they're asking here is determine whether it's 1-to-1. Again, go back to that. The shortest way I could think of to tell you to check, make sure all the x's are different. Make sure all the y's are different. X's, we have a 2, a 3, a -8, and a 6. They're all different. Then when you go to the y's, let's see, we have 9, 6, 14, and -17. Those are all different. And is the function 1-to-1? Yes, because all the x's are different and all the y's are different. That means yes, it is 1-to-1. Okay, moving to number 10 and being asked, again, does this graph represent a function that's 1-to-1? Determine whether f is 1 to 1. Is it a 1 to 1 function? And it is, because here, when you're presented your x's and your y's, here we were given the x's and the y's as ordered pairs. Here those ordered pairs have actually been plotted in graphs, so now it's in graph form, and that's when you should use the horizontal line test. You can draw the horizontal line anywhere you want through the graph, but each time you draw a horizontal line, there should only be one point of contact with the graph. And if there's any more than that, it's not 1 to 1. Okay, but look, no matter where you draw the horizontal line, you could draw it down here, only cuts through the graph once. You could draw it down here, only cuts through the graph once. So, yes. The function represented by this graph is 1 to 1. Okay, going to number 11. So now we take a look at what happens when you have two separate functions and you're trying to prove whether or not they're inverses of each other. You would use this verification procedure. Two functions are inverses if f composed of g of x, and we learned how to do compositions in 5.1. That was the main emphasis of section 5.1. So remember that when you're doing those compositions, did a bunch of these in that section, you open up the front function and you substitute the inner function into that open function. So if f composed of g of x actually turns out to be g composed of f of x, where this time you open the g function and dump f into it, if those both come out to be 1x, you have proven that both of them are inverses. So in the numbers 11 and 12 and possibly 13, we'll see when we get to it, you are going through a three-step process where you're doing this composition in part A, this composition in part B, and then ultimately determining whether or not the two functions were inverses based on the answers that you got here. If they both come out to be x, then yes, these functions are inverses. So here we go. Part A, we're going to do f composed of g of x. So we're opening up this function right here, the f function, which is negative 5 times x plus 5. And we're dumping in the g function into this open spot, which is negative 1/5 times x minus 5. Okay, notice that 5 is the same. I'm going to simplify this first because this is where all the messiness is. 5 is the same as 5 over 1. This 5 in the denominator cancels with this 5 in the numerator. And then negative times negative is just positive, so that's not there anymore. And all you have left in here is 1 times x minus 5, or just x minus 5. Bring down that extra positive 5, continue simplifying. This cancels with this, leaving you with just x. So when we did f composed of g of x, we did get an x. Now if we get an x both times, when we do the composition this way or the opposite way, then we've proven that they're inverses. So it's not enough to just get an x for one of them. Let's go back the other way. This time we're going to do g composed of f of x. So this time f of x is the inner function being substituted into that outer function. So you have to open up the outer function so there's a place to plug it in. Okay, here we go. Opening up the g function, which is negative 1/5 times, and you have an x inside that parenthesis minus 5. Okay, so I always put an extra set of parentheses for the x. All right, now we're going to plug this function into that open spot right there. Okay, so f of x is negative 5x plus 5. Put it right there. I'm going to clean up what's in here first. I see I have a positive 5 and a negative 5 down the way. Those two cancel, leaving me inside this parenthesis with just negative 5x. And on the outside, there is a negative 1/5. This cancels with this because this is negative 5 over 1. Negative times negative, those cancel. and you're left with, I'll just put it right here, negative x, and so you got an x again. Now because you got one x for both of these, f of g of x and g of f of x, then in part C, determine whether functions f and g are inverses. Yes, f and g are inverses. If asked to give a reason why, that comes directly from this procedure. Since f of g of x turned out to be the same thing as g of f of x, which both turned out to be 1x, the process used to verify that they are inverses. So this is the reason why they're inverses. Okay, moving on to number 12. Okay, number 12, same kind of problem, only it has radicals, and you're being asked to find those two compositions in parts A and B, f of g of x, g of f of x, and then use those answers to determine whether f and g are actually inverses. So here's part A. First we're going to do f of g of x. Okay, just remember from 5.1 we learned that we always open the outer function, substitute the inner function. So opening up the f function, it would be x cubed minus 4. And we're dumping the entire g function, not the name of it, the rule, right in here. So cube of x plus 4. Okay, so what you're looking at here is a cube that undoes a cube root. They actually cancel each other. So this cube cancels all of this, and out pops the radicand, which is x plus 4. Bring down that extra negative 4. These cancel, positive 4 and negative 4, leaving you with just x when you perform f composed of g of x. Next, you're going to compose g of f of x. G composed of f of x, which means we will now be opening up the g function, which is cube root of x plus 4, and we're going to dump this f function into that open spot. So we're going to dump in here x cubed minus 4. We can simplify what's underneath this radical by canceling the negative 4 with the positive 4 and seeing that underneath this cube root we only have x cubed. Once again, I'll mention that cubing a term and taking the cube root of a term, they actually cancel each other. So that dissolves the radical and out comes the radicand. So when you did f composed of g of x, you got x, and when you did g composed of f of x, if one of these had come out to be anything other than x, or both of them came out to be something different than x, then they wouldn't be inverses. They both need to come out 1x in order for you to answer yes, they're inverses. Okay, so yes, they're inverses, and you can give the same reason that I gave on the previous page when I did example 11 if they ask for a reason. But this is the reason right here. The composition for f of g of x resulted in x, and so did g of f of x result in x. Okay, example 13. Here, you're just given, this is a pretty easy problem, you're just given a graph. They're showing you specific points for the original graph. This is the original graph where they plotted 2, 5, 1, 2, negative 2, 0, and negative 3, 3. And they want you to come up with the inverse graph. So what makes this easy is that they've already given you the points. And once again, remember that the relationship between the original function and the inverse that we are expected to come up with, the x's and the y's switch responsibility. So if in the original function you have 2, 5, 1, 2, negative 2, 0, and negative 3, negative 3, Then if you want the points that are on the inverse so that you can see the mirror image on the other side, you just switch the x and the y. So from this point, we would switch them around, and we would likewise do the same thing for each one of these. Switch this pair around, switch this pair around, and this pair, you know, no matter, even if you did switch it, you're going to get the same thing just because it's the same identical x and y. Now go plot this second set of points, the points on the inverse, and you'll see that you have mirror images on either side of the line, y equal to 6. So this would be 1, 2, 3, 4, 5, up 2, plot the point. Go up to 2, 1, go to 2, 1, plot another point. 0, negative 2 would be right there, and then negative 3 is already plotted. Connect the points. Okay, notice that if you were to fold your paper right here and fold this image right here on top of that one, they would superimpose. Okay, going to the last problem, which is example 14. And this time, you're going to come up with your own inverse. So, this is the first problem where you get to do this. You have a single function, not two functions, and you're going to create your own inverse. So there was a set of steps on the previous page. They're down at the bottom. So I collected those steps for you here, but I'm going to put them in my own simple language and demonstrate them. Not that they didn't give an excellent explanation, but sometimes I just use terminology that maybe is not so easy to understand. So, example 14. Okay, it says in part A, find the inverse, check your answer. You can check that twice, but we're just going to find the inverse. So we're starting off with f of x is equal to 12x plus 4. Okay, so step 1 is to replace the f of x notation with y. You need just a plain x and a plain y. Okay, so doing that, we're going to replace this with y, copy the right-hand side of the equation. Step 2, we're taking a single function and finding its inverse. Switch the x and the y. Remember, that is the main part of the relationship between a function and its inverse. So if you're switching x and y in this equation, that's why you needed a y, so that you would see where the y is instead of that f of x notation. So this is going to become an x, this is going to become a y. Okay, third and final step. You're going to solve for your new y. This is the new y. It used to be an x, so it's the new y. Solve for the new y. Okay, that means we're going to be trying to isolate this y variable right here. And that means I'm going to pull the 4 over here. It's going to become x minus 4. While leaving the 12y there, I'm going to divide that coefficient off of the 12, off of the y, so that I can completely isolate the y. You can write this as two separate terms just so just to make it easier to graph. So if I separate it, it looks like that. And I'm going to make it even more ready for graphing. Okay, so I divided both sides by 12. That got rid of this, isolating the y. That gives you x over 12 minus 4 over 12. Coefficient in front of that x is 1, so that 1/12, if you remember how to graph a line, straight line. This is your slope. This is the rise. This is the run. Always the coefficient of your x term. Top is the rise, bottom is the run. And then this negative 1/3. That negative 1/3 that has no variable associated with it, that's called your y-intercept, and it is where the graph starts. That's the easiest way to graph, by knowing what's the y-intercept and what is the rise and what is the run, so that you don't have to make a table of values. This is where the graph starts. Okay, and by the way, once you solve for that new y, that is the inverse. So you can write it like this: y is equal to, or you can write this with an invert. You can replace this y with an inverse symbol. So once you state what y is, after doing all these steps, you're stating the inverse in terms of x, and there is that inverse right there. So I'm going to leave it like that. Then the original is up here. See, it had a coefficient. I'm going to put both of them right here just so we can look at both of them as we're graphing. We had the original function, which was 12x plus 4. This is your y-intercept on the original function, and this 12 over 1, well, that's the rise, that's the run on the original function. Then we had the inverse, and that turned out to be y is equal to 1 over 12x minus 1/3. Again, we had a y. We recognize what the y-intercept is, so we can start the graph there. And then we recognize that the coefficient is the slope. The coefficient of x is the slope. Top is the rise, bottom is the run. So let's just graph one graph at a time, and then recognize that both the original graph and the inverse are mirror images on either side of the line called y equal to x, which is just a line that goes right through, slanted line that goes through the origin and has a slope of 1. Okay, coming down here, let's graph both of these. Okay, so I'm going to start at 4 for that first graph, and I'm going to rise 12 and then run 1 to get the other point. I only need 2 points. I already have 1. I need 2 points to connect so that I can create my line. Anything that is first degree in both your y and x is a line. Okay, so let's see. If I go up 12 from 4, I'm at 16. Now run 1, and then you're going to connect those 2 points. Let's see if I can get these lined up. Not too good at that. Okay, so this represents the original function, and you can write f or you can write f of x, whatever you prefer. Now I'm going to go after the other one. Okay, the other one is, let's see, we would be starting at negative 1/3. So negative 1/3, let's see. If I go down to negative 1/3, I can't even go to negative 1. I could barely move below the x-axis, so it'd be like right there. I know that looks like the halfway point, but that's the best I can do. That looks like 1/3, and then I'm going to rise up 1 whole block. So if I'm starting off slightly below a horizontal grid mark, which is called the x-axis, when I move 1 for my rise, I'm going to land in a similar position right below the horizontal grid mark. So go up 1, right below that horizontal grid mark, but then let's see, what's the run? We're rising 1, and we're running 12. So I'm right here at negative 1/3, rise up 1, still below that horizontal mark, and we're going to run 12, all the way to 12. So about right there. Nice estimate of what the graph looks like. So let's see. I had negative 1/3 and this. Trying to connect those to make a decent line. Okay, so this line represents the inverse. Okay, notice that if I was to draw my line called y equal to x, which is just a slanted line with a slope of 1 that goes right through the origin. See, and you have mirror images. If you were to, This is the line called y equal to x. If you were to crease your paper right on this line right here, and then fold this graph, just take these two pieces and fold it on top of this, then this graph right here would superimpose on that piece of graph. That's if you were to fold the paper here, pick this up, and fold it over. This would superimpose on top of that. Again, that's always going to be true of the original function and its inverse. Okay, that completes section 5.2.